Okay, so first let me briefly remind you of how this online seminar works. So basically, please mute yourselves during the talk, but you are encouraged to turn on your video if you feel comfortable. So because it just feels nicer that way. And if you have any questions during the talk, you can type those questions in the chat box. If it's a quick question, I may interrupt the speaker to ask. But today we also have a collaborator of the speaker who will monitor the chat box, and he will probably answer like the questions there. Or you can also ask the questions directly to the speaker during the question break, or like in the Q&A session at the end of the talk. So the video, the talk video will be recorded, and it's also being streamed online in YouTube. If you don't want to appear in the video, please mute yourself or like turn off your video, or you can also watch the live stream on YouTube. The slides are available on the website, and I'm also going to paste the link to the slides today in the chat box. Okay, so that's for the logistics. So today we are really happy to have Jing speak. Jing is an associate professor at the Decision Risk and Operations Division of Columbia Business School. Her research is at the interface of applied probability and service operations management. She also develops efficient simulation algorithms to facilitate better decision-making in complex stochastic systems. She received her PhD also from Columbia in operations research. So before joining Columbia Business School, she was an assistant professor at the Northwestern University. She is going to talk to us today about the spectral gap of replica-exchange Langevin diffusion. So let's welcome Jing. And Jing, feel free to get started.
Okay. Thank you, Wena, for the kind introduction. And thank you all very much for being here today. So first of all, I would like to thank the seminar organizers, Wena, Christina, Debunker, and Siva, for putting together this wonderful seminar series. I feel this truly brings us closer together at these challenging times. All right, so for the talk today, I would like to talk about how to quantify the efficiency of a sampling method called the Replica-exchange Langevin diffusion. And our task here is to sample from a target distribution that has multiple modes, and each of these modes are sort of isolated from each other. This is joint work with Xin Tong from the National University of Singapore. And as Wena mentioned, Xin will also be joining the talk today, and he will help me handle questions in the chat box. So my talk today contains three parts. I would like to start by giving a brief overview of the Replica-exchange Langevin diffusion, which I think is a very elegant and powerful sampling tool. Okay. And then I will dive a little bit to talk about how to quantify the efficiency of this sampling method. And for the last part, I would like to talk about at a high level how this idea of replica exchange can be applied to other applications. Now, for most part of today's talk, I would like you to think about our objective here is to sample from a target distribution that has multiple modes. For example, we can think of our target distribution as a mixture of log-concave densities, and each of these log-concave density have a different mode. Or you can think more broadly as the energy landscape of my target distribution, which I denoted by the capital H function here, is a smooth but non-convex function. So Langevin diffusion is actually one of the main workhorses for this type of sampling task. In particular, I'm going to consider a diffusion process whose drift term is the gradient of the log density function here. And the diffusion coefficient is a constant square root of 2. Under suitable regularity conditions, this diffusion process will have a stationary distribution that is exactly the target distribution that I'm interested in. And because to run this diffusion process, I only need to know the gradient of the log density function here. So it often do not require knowledge of the normalizing constant of my target distribution. And this overcomes the difficulty in a lot of the sampling tasks in practice. Now, let's think a little bit about how to quantify the efficiency of this sampling method. Right? So what we are eventually interested in is pi, which is the stationary distribution of this diffusion process. But when running it, we are likely to start this diffusion process from an arbitrary state. So roughly speaking, the efficiency of this method can be think of as how fast this diffusion process converges to stationarity. And I'm going to quantify the convergence rate here using the spectral gap. The inverse of the spectral gap can be defined as the infimum of the ratio between the expected value of the Carré-Duchamp of my underlying stochastic process and the variance. The nice thing about the spectral gap is that it translates the problem of analyzing the ergodicity of the underlying stochastic process to some functional analysis of partial differential equations, which could make the analysis a lot more tractable. And to see why the spectral gap can be used to quantify the convergence rate here, I'm going to denote mu t as the distribution of my stochastic process at time t. Then the chi-squared distance between mu t and the stationary distribution pi satisfy this bound, which basically says that mu t gonna converge to pi exponentially fast at rate 2 times kappa inverse, where kappa inverse is what I refer to as the spectral gap here. So we see that the larger the value of the spectral gap, the faster this stochastic process converges to stationarity. Now let's look at some concrete examples. My first example here, my target distribution is just a simple Gaussian density. So phi here is the density function of a standard Gaussian distribution. And I'm going to scale x by 1 over epsilon here. So what the role the epsilon plays here, by 1 over epsilon here. So what the role the epsilon plays here is that the smaller the value of epsilon, the higher the concentration this density has around its mode. In this case, Langevin diffusion can be a very efficient sampling scheme. More specifically, we can show that the spectral gap of my Langevin diffusion is lower bounded by epsilon to the power minus 2. So we see that the smaller the value of epsilon, the higher the concentration of this density is, and the faster my diffusion process is going to converge to stationarity. Now let's look at a slightly different example. In the second example, instead of interested in a single Gaussian, my target density becomes a mixture of 2 Gaussian. And the only difference between these 2 Gaussian is that they have different mode. My first Gaussian here has its mode at the origin, and my second Gaussian here had its mode at M, where M is different points than the origin. In this case, Langevin diffusion can actually become quite inefficient. In particular, I can show that the spectral gap in this case is upper bounded by this quantity here. And if I have a very small value of epsilon, then this can lead to an extremely small spectral gap in this case. So to see intuitively what is happening in my second example here, right? Let's try to draw the density function of my second example. So here, my second example essentially have a bimodal density. I'm going to denote the first mode as M1 and the second mode as M2 here. Now, if I initialize my diffusion process somewhere around the first mode, let's say I initialize my diffusion process here, right? The drift term, which is the gradient of the log density function, will very quickly drive my diffusion process to the first mode. Okay. And then it will keep circling in some small neighborhood around the first mode here. Okay. And because the stochastic force is not strong enough here, and because there's a strong force imposed by the gradient term, right? So it is actually going to be very hard for my diffusion process to escape from this first mode and move to the second mode here. So basically, my diffusion process is likely to be trapped around the mode where it is initialized from for a long time before it can actually move to the second mode. And this slow movement among different modes is essentially what slows down the convergence rate of my diffusion process. Now, a natural idea to try to facilitate easier movement among different modes is to say that I can just inject more stochastic noise to my underlying process, right? So one way to do that is instead of using the square root of 2 diffusion coefficients, I can increase the diffusion coefficient to some larger number, which I denoted by square root of 2 times tau here. And I'm going to refer to the parameter tau as the temperature of my Langevin diffusion. Okay. The higher the temperature, the more stochastic noise I injected to this diffusion process. Now, under this new Langevin diffusion, the stationary distribution is actually proportional to the original stationary distribution raised to the power 1 over tau. Okay. So what this tau do here is that if I impose a larger temperature, it essentially flattens my target distribution. So it brings the peaks lower. And that is essentially what facilitates easier movement from one mode to another. However, this distribution, this stationary distribution of this high temperature Langevin diffusion is no longer the target distribution that I'm interested in, right? So instead of running this high temperature process by itself, I will actually end up running 2 processes in parallel. The first process, which I denoted by X here, is my original unit rate Langevin diffusion. Okay. And the second process, which I denote by YT here, is a Langevin diffusion that is running at a higher temperature tau. I also add an extra term to the drift term here, and that is mostly to ensure the positive recurrence of this high temperature process regardless of what temperature I use. So what this extra term is doing is that whenever the stochastic process drift away from the central region where I'm interested in, there's enough force to drive it back to that region. And of course, I cannot just run these 2 diffusion processes in parallel independently, right? This will not be different from running the first process by itself. So instead, I have to think of some way to let the 2 processes collaborate with each other or communicate with each other. And this is exactly where the replica exchange idea kicks in. More specifically, I will be proposing this swapping event or exchange event according to an exponential clock with rate rho. Okay. And this is an independent exponential clock of everything else. Whenever my clock rings, I will try to exchange the position of my X and Y process according to a Metropolis-Hasting type of rule. More specifically, the exchange probability gonna take this particular form. Now, under this exchange mechanism, the good thing is that the stationary distribution of my diffusion process still takes this product form. Okay, if I look at the marginal distribution of the XT process, it is still the target distribution that I'm interested in. To see intuitively how having this extra exchange mechanism can help me speed up my convergence, okay, let's go back to the picture we started with. Recall that if I only run the XT process, right, it will likely be trapped on one of the mode where it starts with. And I'm going to denote the high probability ball around this mode as BM1R. So R is essentially the radius of the high probability ball around the first mode here. If I start my XT process around M1, then XT will keep circling inside this ball. And it's very hard for the XT to move from this ball to the ball around its second mode. On the other hand, because my YT process is running at a much higher temperature, so my YT process can be more freely circling around a larger region, which I denoted by a larger ball, which is B0 with radius capital R here. So capital R can be think of as a much larger radius than the little ball around each mode. Okay. Now, if my YT process happened to be in the small area around the second mode, okay, if the YT process happened to be inside the ball M2 little r here, then with very high probability, my swapping will be a success, meaning that this swapping probability is very likely to take some value that is close to 1. Okay. And then by exchange the position of XT and YT here, I help move my XT process out of its current mode and transition to another mode. Okay. And this is what is essentially speed up the convergence rate here. However, there is a potential drawback of this algorithm that I just described. The drawback is that now my YT process can more freely move around a much larger area. Okay. So the probability that my YT process will actually be inside the little ball around the second mode could be very small, especially when the little r is much smaller than my capital R here. And this would mean that if my YT process is not in this high probability ball, then in a lot of the cases, the attempted swapping event will actually be a rejection. So I wouldn't really do the swapping between my XT and YT process. Now, a way to further overcome this challenge, right, to have more successful swapping event here is actually to run more than 1 copies of Langevin diffusion in parallel. So in this picture, instead of the YT process and the XT process, I also added an intermediate process, which I called X1T here. So I changed the notation a little bit. Now my XT process is denoted as X0T, and my YT process is denoted as X2T. And I add an extra Langevin diffusion, which I called X1T. And you can think of the temperature of this X1T to be somewhere between 1 and tau. So between my low temperature process and my high temperature process. Now let's first look at X1T and X2T. Right? X1T has a much larger high probability ball than the X0T process. This means that it's more likely for my high temperature process to be inside some high probability ball for the X1T process. So the exchange between X1T and X2T going to happen more likely. Okay. Similarly, for my X1T process, it's much more likely to be within the small ball around the second mode for my X0T process, which also implies that the exchange event between X0T and X1T going to also happen more likely than in the previous plot. Okay. And this is essentially what can help me overcome the challenge I described in the previous slide and inject more successful swapping event between these processes. And because of the mechanism I described here, for most part of the talk, when I'm running multiple copies of Langevin diffusion, I will try to inject these swapping only between the processes with adjacent temperatures, because we see that the swapping between processes with adjacent temperatures are more likely to happen than processes with temperatures that are far away from each other. Now, this is the basic setting of replica-exchange Langevin diffusion. So I would like to pause a little bit here and see if there's any questions from the audience.
I have a question. So normally you would try to implement this in discrete time, right? Mm-hmm. So how would that affect the accuracy? I mean, so here you're computing spectral gap and everything, assuming it's a diffusion. Mm-hmm. When you discretize it and so on, does that affect the answer somehow? Or what is the role of discretization here?
Yeah, so that's a very good question, but I will hold that question a little bit because I will answer that in a few slides.
Okay, Thanks.
We didn't fully address the discretization issue, but you will see where the complexity of the discretization will come into play in a few slides.
There's another question in the chat box. Ganesh, maybe you can just speak directly.
Okay.
Yeah, hi. Is there any connection with reversible jump MCMC of your method?
Yes, so this replica-exchange Langevin diffusion is a fully reversible diffusion process. So that's why I still have that nice product form stationary distribution. So yeah, it's a special case of reversible jump MCMC.
Okay, thanks.
Okay, so I will move on. Okay, so the research question we would like to address in our work is to quantify exactly how this replica exchange mechanism is helping us speed up the convergence. And having such quantification will also provide us with guidance about how to set the temperature of my high temperature process and how to set the swapping intensity in implementations. We will further quantify the spectral gap when we are running multiple copies of Langevin diffusion. And this will tell us exactly what benefit these extra copies of Langevin diffusion is bringing to us, and also how to space the temperatures of these different Langevin diffusions and how to set the swapping intensities in those cases. So despite a long history and a lot of literature on the replica exchange Langevin diffusion, the questions that I listed here are actually largely remain open. Now, before I present our main result, let me first give a brief overview of the related literatures. So most Markov chain Monte Carlo method suffers from a slow convergence rate when the target distribution is meta-model with isolated mode. And the reason is exactly the same as what I described before. So it's very hard for my Markov chain or Markov process to escape one mode and move to another mode. And the replica exchange idea, which is actually also known as the parallel tempering idea, has been proposed in the literature to exactly address this challenge. And it has seen successful implementations in various applications contexts. The key question in implementations of this algorithm is how to tune the hyperparameters. So in particular, how to set the temperature and how to set the swapping intensity. And there are actually very few theoretical results quantifying these hyperparameters. So most of the previous work focused on using simulation experiments or heuristic argument to say how we should set these parameters. There are a few exceptions, and I listed the most related theoretical investigations in blue here. So what I highlighted in blue are actually theoretical investigations of this problem. For example, the work of Woodard et al. 2009, they actually provide a lower bound for the spectral gap of replica exchange Markov processes. Okay. And there they provide some guidance about what type of target distribution would be this method be good at sampling from. And the work of Dubois et al. In 2012 actually derived the large deviation rate function for the empirical distribution of replica exchange Langevin diffusion. And by looking at that large deviation rate function, we see that the larger the swapping intensity, so the more often we propose those swapping events, the larger the large deviation rate function gonna be. And the last work here, which is the Roberts and Rosenthal 2014, they try to look at what is the optimal way to set these temperatures so to achieve the optimal acceptance probability in these swapping events. Okay. But their analysis rely on large dimensional limits of the process, and they assume the process is already in the equilibrium mode. So they only look at the equilibrium mode behavior of the processes. In contrast, our analysis relies on these concrete diffusion processes, and we actually characterize the non-equilibrium behavior of the process. So ideas similar to the replica exchange has been proposed in the literature. For example, the simulated tempering is a very similar idea. Instead of running multiple copies of Langevin diffusion in parallel, they would just run one copy of the Markov process. but they would change the temperature of this macro process according to a Metropolis-Hasting type of rule. Okay. The saving they have there is that you'd only need to run one diffusion process, but the cost they have to pay there is that whenever you are trying to exchange the temperature of this processes, you need to know, in order to evaluate that exchange probability, you actually need to know the normalizing constant of your underlying density function. And another similar idea is called sequential Monte Carlo, where the idea is that I will propose a sequence of distributions that are easier to sample from. And by moving along this sequence, I will eventually get to the hard to sample from target distribution that I'm interested in. Our theoretical development is closely related to the literature on quantifying the spectral gap of diffusion processes and also the Poincar inequality. So before I present the actual theoretical results, I would actually like to spend a few slides talking about the Poincar inequality here, which is actually one of the key tool sets in our analysis. A distribution pi is set to satisfy the Poincar inequality if this inequality holds here for any smooth enough function f. And the kappa is often referred to as the Poincar inequality constant. Now, for Langevin diffusion, there is a nice connection between Poincar inequality and the spectral gap. Okay. In particular, recall that the inverse of our spectral gap is defined as follows. Okay. So which basically says that the tightest constant here that would make the Poincar inequality hold is exactly the inverse of the spectral gap of the Langevin diffusion with stationary distribution pi. A nice thing about the Poincar inequality is that it can actually be verified by constructing an appropriate Lyapunov function. So instead of deriving the Poincar inequality constant directly, we can first try to construct an appropriate Lyapunov function, and then the constant can be derived from parameters of that Lyapunov function. Okay. More specifically, a function v is called the Lyapunov function for our target distribution pi if it satisfies the following two conditions. So the b here can be interpreted again as the high probability ball around the mode of the distribution pi. And the first condition here essentially says that whenever my diffusion process is outside this high probability ball, there's enough force to drive it back into the ball. And the second condition here requires that my target density is properly bounded inside this high probability ball. Now, under these two conditions, we can actually have an explicit form for the Poincar inequality constant. In particular, all the parameters in this formula only depends on my Lyapunov function. Now, to see a concrete applications of this property, we note that if the distribution pi is a log-concave density, then we can construct the Lyapunov function as follows. Okay. So A here is the log-concave parameter of my density, and the D is the dimension of my problem, and M is the mode of this density. Okay. And by having this Lyapunov function, we can further show that the Poincar inequality constant is upper bounded by this formula here. So now we are ready to talk about our main result. Okay. And the first question I would like to answer here is, what type of target density would the replica exchange idea be good at sampling from? So we first note that by having this high temperature process and swapping the position of the high temperature process with the low temperature process, we're only helping this low temperature process to jump from one mode to another. But it doesn't really help the low temperature process explore local mode more efficiently. So the first condition we impose here is essentially requiring that the low temperature process by itself should be good at sampling from local mode. In other words, if I view my target distribution as a mixture of a bunch of density functions, then I require each of these component density function vi to have a proper Lyapunov function. So this is saying that if I'm not viewing the mixture distribution, but I'm only looking at each of this component distribution, then my Langevin diffusion should be good at sampling from this component distribution by itself. If these VIs are log-concave densities, then it satisfies assumption 1. But assumption 1 is more general than saying each of these component densities are log-concave. Now let's look at the role of my high temperature process. Right? My high temperature process is helping me move from one mode to the next. So what I have to impose on this high temperature process is that it by itself, it should be good at exploring the state space. So it should be efficient to move from one mode to another. And this is what essentially my assumption 2 is requiring here. Okay. My assumption 2 says that the stationary distribution of my high temperature process should have a proper Lyapunov function around each of the mode mi. And what this essentially implies is that my high temperature process should be good at moving around these different modes by itself. I would also like to comment that for my high temperature process, okay, it doesn't really need to have the same drift function as my low temperature process. So I can actually design it to have a different drift function than the low temperature process. But if it does has a similar drift function as my low temperature process with this extra regularization term I talked about before, then we can show that by properly choosing the parameter capital M and the temperature tau here, this high temperature process do satisfy my assumption 2 here. Now, to sum up the first two assumptions I've discussed so far, okay, our first assumption requires that each component density in my mixture model satisfy a proper Poincaré inequality with Poincaré inequality constant little q here. And my second assumption requires that the stationary distribution of my high temperature process satisfy an appropriate Poincaré inequality with constant capital Q here. And each of these Poincaré inequality is built around the high probability ball, right? In the high probability ball around the mode. And the capital R and the little r here are essentially the radius of these high probability balls. And my third assumption requires that the radius of these high probability balls to be suitably bounded. Now, under these three assumptions, we can actually show that the inverse of the spectral gap, which is my kappa here, can be shown to be of this order. Okay. In particular, the Q here is the Poincaré inequality constant of each of my component density. Tau is my temperature, and rho is my swapping intensity, and R is the high probability ball, is the radius of the high probability ball around each component density or around each individual mode. To see how to interpret this bound here, right, let's move back to our example 2, where I'm interested in a mixture of two Gaussians which is concentrated around two different modes. Now, in this case, we can actually show that the radius of the high probability ball is of order epsilon, and the Poincaré inequality of each of these individual component density is of order epsilon square. Okay. In this case, if I choose my temperature and my swapping intensity to be larger than r to the power minus d, then I can actually achieve a constant spectral gap. Okay. This is to be compared to when I'm running the Langevin diffusion by itself, where the spectral gap can be upper bounded by this small number here, which actually depends on the value of epsilon. Okay. If I further increase my temperature and my swapping intensity to be larger than Q inverse times r to the power minus d, then I can actually have a spectral gap that scales as epsilon to the power minus 2. So this is the same as the spectral gap for each individual density here. So we see that by properly tuning the temperature and the swapping intensity, we can actually make the spectral gap independent of the epsilon parameter here. However, we also see that because I require, let's say, to achieve a constant spectral gap, right? I require the temperature and the swapping intensity to be larger than R to the power minus D. And this is essentially saying that the temperature and the swapping intensity need to be of order epsilon to the power minus D. Okay. And as Stricken mentioned at the very beginning, that when I implement this algorithm, I often cannot run this continuous time diffusion process. I have to do some form of discretization. If I have a very high temperature and a very large swapping intensity, this essentially says that I have to run this discretization at super tiny discretization step sizes. I have to take baby steps when I do the discretization. And this could substantially increase the computational complexity in implementations of this method. Now, I also mentioned that one way to sort of further improve the efficiency of my algorithm is to run multiple copies of Langevin diffusion in parallel. So here I'm going to denote my original Langevin diffusion at unit temperature as x0t here. And I'm adding k extra copies of Langevin diffusion running at higher temperatures. And I'm going to order the temperatures such that tau 1 is less than tau 2 is less than tau 3. I'm going to impose exchange events between two processes with adjacent temperatures according to an exponential clock with rate rho. And whenever this clock rings, the exchange is going to happen according to a Metropolis-Hasting type of rule with this exchange probability. Now, by having this set up, I can actually show that the inverse of the spectral gap kappa here can be shown to be of this order. Okay. The Q naught is the same as my Q before. It's the Poincar inequality constant of each of my component density. Tau k is the temperature of the case Langevin diffusion. Rho is my swapping intensity. And the RK here is the radius of the high probability ball for the stationary distribution of the case Langevin diffusion. Now, to see how to interpret this probability bound, this spectral gap bound here, okay, let's go back to our example 2. We've already seen that the radius of each component density here is of order epsilon, and the Poincar inequality constant is of order epsilon square. In this case, if we choose the sequence of Langevin diffusion in a way that the radius of their corresponding high probability ball grows geometrically at rate epsilon to the power minus 1 over k, then we only require the temperature and the swapping intensity to be larger than epsilon to the power minus d over k. Okay. So the extra d divided by k term is essentially how, by running multiple copies of Langevin diffusion, is helping me reduce the requirement on my temperature and the swapping intensity here. And in this case, I can still achieve the constant spectral gap. So to summarize the idea at a high level, right, we see here the replica exchange idea essentially provide a good collaboration mechanism between my processes. So my low temperature process are now focusing on exploiting component densities or exploiting local structures, while my high temperature process is moving around the state space and try to facilitate movement from one mode to another for my low temperature process. And that is essentially what could speed up the convergence of this algorithm here. Now, I would like to pause a little bit here and see if there's any questions from the audience.
I have a question about the Y process that you defined in the beginning. You introduced a second term that brings you back to origin. What's the motivation for that, and how does that connect to the theorems that you stated?
So I need my high temperature process to be suitably ergodic, in the sense that regardless of how large the temperature I use, I don't want it to diverge away from the central area where I'm interested in. So if I do not impose an extra regularity term, but if my underlying density, if my target density is regular enough, that might work. But this extra term is saying that if my underlying density is not regular enough, there's an extra force I added to drive it back to the central region. So that's intuitively how that term works.
Got it. Thanks.
David, do you want to just speak up?
Sure. So yeah, I have a few questions. So the first question is, yeah, that goes back to my previous spectral gap question. So just to be clear here, you're saying that as K gets large, the thing is behaving nicer, even though the dimension of the process whose spectral gap you're bounding is diverging, essentially. Is that accurate?
Even though the dimension is divergent. What do you mean by the dimension?
Yeah, so I guess one thing I'm confused about is like, so when capital K is large, right?
Yes.
When you talk about the spectral gap, you're talking about the gap of then the high dimensional thing, which is these capital K processes. Is that accurate?
Exactly, yeah. How these K dimensional processes converge to stationarity, yeah.
Okay, so just to be clear then, you're saying that as capital K gets larger, even though that's a higher dimensional process, it is still true that it is converging faster, even though the dimension is higher.
Yeah, so in terms of, if I only care about the convergence rate to stationarity, then yes, if I run these higher dimensional processes and when I tune the parameters so that they satisfy the requirement I impose here, then I can achieve a fast convergence rate. But I guess what you are sort of hinting is that when I'm running this higher dimensional process, it might also increase my computational complexity, right? It's not only about how fast they converge to stationarity, but I have to keep track of multiple copies of these Langevin diffusions in parallel. So I guess from the total computational complexities perspective, when I'm trying to see, it's not only about the convergence rate, I also have to take into account running these extra copies, the cost of running these extra copies into account. For that, we didn't look into that. I actually list this as an interesting future research direction. So people could actually do a more close analysis to see from the computational cost perspective, what is the optimal extra copies to run. And here I'm only quantifying how it helped me speed up the convergence rate to stationarity.
Cool. One other question that maybe relates to that, although maybe it doesn't. So do you need to know the modes in advance to like initialize this or no? Is it?
No, I don't.
Okay, and I guess this, or the similar question would be like, do you need to know these Lyapunov parameters, and can you infer them from watching a process or from samples in some way? Or how should we think about, to be more concrete maybe, does your chain need to know those Lyapunov parameters? And if so, how do you avoid kind of a chicken and egg? We needed to know those parameters to run the chain, but maybe you wouldn't know those parameters or something. Okay,
that's a good question. So for running the Langevin replica-exchange Langevin diffusion, I don't need to know those parameters. And I don't even know, even though I assume like my target density can be decomposed into a bunch of component density, right? I don't even know what that decomposition looks like. So I only require that I can evaluate my target density up to not knowing the normalizing constant. So that is what essentially requires to run this replica-exchange Langevin diffusion. However, as I mentioned here, right, in order to set the optimal temperature and the optimal swapping intensity, I do require a little bit of extra knowledge of my underlying process. In particular, in order to have a constant bound for the inverse of the spectral gap here, right, I want to make sure that my temperature and my swapping intensity are properly chosen so that it cancels out the effect of this differences between these radius of the high probability ball here. So this do require a bit of extra knowledge of these Lyapunov function construction or high probability ball. But I would say the key insights here is that I should sequence my temperatures in a geometric way. So to make sure that these radius are growing geometrically. But in practice, how exactly you're going to form those geometric sequence could be up to a further fine tuning as you run the process. Okay, and for my if I'm only running 2 copies of Langevin diffusion, then I also require knowledge of this component radius of this each component density, right? And this also would rely on some knowledge of the underlying processes. Yeah.
Okay, thanks a lot. Thank you.
Okay. All right. So for the very last part of today's talk, right, I would like to just talk at a more high level how this replica exchange idea can be applied to other applications. What I like this idea a lot is because I feel it truly provides such a simple yet powerful mechanism to start facilitate collaborations between different algorithms. Right? We can think about like maybe different algorithms would have different areas of expertise and how we could actually let them work together to achieve a task in a more efficient way. And I feel this particular idea, the replica exchange idea, is essentially creating such a collaboration mechanism. To put this in more concrete terms, I'd like to talk very briefly about another application of this idea. So for the second application, I would like you to think about our objective here is to solve a non-convex optimization problem. Okay? In particular, my objective function f is a smooth but non-convex function with many local minimums. And my goal here is to find the global minimum of the f function here. I'm going to consider a similar idea as the replica exchange Langevin diffusion. So in particular, I will run a low temperature process and a high temperature process in parallel. Now, for my low temperature process and high temperature process, I'm going to change the drift term to be the negative of the gradient of my objective function. Okay. And I'm also going to push the low temperature process to the extreme that I'm going to actually push the temperature to 0, which essentially reduces to a deterministic process. Let's first look at these 2 processes independently in isolation. Okay. For my low temperature process, it is essentially an ODE. Okay. In actual implementations of this process, I often cannot run this continuous process exactly. Instead, I will run a discretized version of this process where I'm taking a simple Euler discretization scheme here. And the H is what I refer to as the step size of my discretization. Okay. And if you look at this formula, this is essentially the formula of gradient descent. So what I'm running as the low temperature process is essentially a gradient descent. We know that for gradient descent, if the underlying objective function f is strongly convex, then it can actually converge to the global minimum exponentially fast. So when I have enough regularity structure on my underlying objective function, gradient descent can actually be a very efficient algorithm. However, if my objective function is not convex, then gradient descent can be trapped in local minimums or even saddle points. On the other hand, my high temperature process, right? And again, I cannot run this continuous time process in most cases. Instead, I will implement a discretized version of this process where h is my step size and tau is the temperature here. And the zn's are just the IID Gaussian random variables. Now, by adding this Gaussian noise, it will help this process escape local minimums or even saddle points, right? But the challenge here is that because of this added stochastic noise, in order to achieve convergence to the global minimum, I need to make sure that the step size and the temperature here are properly tuned with respect to the accuracy level I want to achieve. Okay. More specifically, if I want to achieve an epsilon accuracy, if I want to be epsilon close to the global minimum, then I actually need to set the temperature and the step size to be very small or proportional to some order of epsilon. And this could substantially slow down the convergence rate or increase the complexity of my algorithm here. And this is essentially what's going to happen if you run just these two processes in isolation. Now, let's go back to the replica exchange idea, right? I'm going to inject the replica exchange idea to sort of allow these two to communicate with each other. In particular, at every iteration, I'm updating my xn and yn process. I'm going to check the objective function evaluated at x and y. And if my y here yields a lower objective function than my x, then I will just swap the position of the two. So what this swapping is doing here is essentially saying that if I start my xn process around one of its local minimums, then I know the gradient descent is very efficient at exploiting local structure. So very quickly, my xn process would be able to find the local minimum of that region. On the other hand, my yn process is running at with stochastic noise. So it's very good at exploring the state space. Whenever my yn process finds a better local minimum than the local minimum that my xn process is currently at, then the yn process is very likely to yield a lower objective function than my xn process. And by doing the swapping, I'm essentially moving my gradient descent to a better neighborhood to start its exploitation. So in this case, by allowing the collaboration between the two, we can show that under proper regularity conditions, the complexity of this algorithm is only log 1 over epsilon. So it's basically the same as running the gradient descent to solve a strongly convex objective function. And the extra benefit I would like to highlight here is that now because of this collaboration, they only need to focus on the task they're good at. So the high temperature process is only in charge of exploration, and the low temperature process is only in charge of exploitation. So I have much less requirement in terms of tuning the parameters of these two processes. More specifically, I don't really require the step size or the temperature to depend on the accuracy level I want to achieve. I only need the temperature to be of constant size and the step size to be less than 1 over 2L, where L is the Lipschitz constant of the gradient of my objective function here. So we see that by allowing this division of labor, we actually have much less requirement for tuning the parameters. And indeed, in our numerical implementations, this algorithm is able to achieve consistently good performance. Now, I would like to conclude my talk today with two interesting directions for future research. The first interesting direction is actually also related to the question David asked and Striken asked. So if we look at these multiple copies of Langevin diffusion, right, we actually have quite some flexibility of choosing what are the drift term of these higher temperature processes. Then an interesting research question would be, is there an optimal notion about how to choose the drift term here? Okay. Is there an optimal design in terms of the drift term of my high temperature diffusion process here? And there are two main considerations we have to think about when designing these high temperature processes. The first thing is that, of course, we want to be able to make sure that we still achieve the higher convergence rate for the underlying high dimensional diffusion process. But the second consideration is that I should be able to sample these processes, right? Sampling these high temperature processes shouldn't be more difficult than sampling from my target distribution itself. So in particular, I should be able to get explicit access to these extra diffusion terms. Or even I can have direct access to the stationary distribution of this high temperature process. If that can be done, then I can save the computational cost even more, because I don't need to run the Markov chain. I can sample directly from its stationary distribution. So I think how to optimally design these intermediate Langevin diffusions would be an interesting future research direction. And of course, in actual implementations, it also involves discretizations of these continuous time processes. So how to do the discretization in the optimal way would also be very interesting. For example, one thing I could think of is that maybe I don't need to use the same discretization step for these different processes. So maybe I can use like a multi-level idea. For some levels, I need to run it at a finer grid, while for other levels, I can tolerate more estimation errors. So how to properly design these would be very interesting future research directions. And the second research direction is going back to this more broad idea of the replica exchange method. Right? As I mentioned before, I feel like this provides a very good mechanism to allow collaboration between algorithms. And for this talk, I discussed one particular collaboration, that is a collaboration between gradient descent and Langevin diffusion. But more broadly, how can we use this idea or similar idea to allow collaborations between deterministic optimization algorithm and sampling-based method to achieve better outcomes? I think would be a very promising future research direction. That's all I want to discuss today, and I'll be happy to take questions. Thank you.
Yeah, thank you, Jing. And now, now is the Q&A session. You can just raise your hand. Siva, go ahead.
So I have a couple questions. So the first one is about the collaboration between gradient descent and Langevin dynamics. I'm sorry, maybe I missed. What are the results there? Are the rate of convergence known, and their comparison to like prior algorithms and so on?
Yeah. So if I'm running the Langevin diffusion by itself, then the best convergence rate is roughly of this order. Right? It's roughly epsilon to the power -1 times log 1 over epsilon. But there is a little bit of extra caveat because what they are quantifying is this term, but you also need to tune the temperature appropriately in this case. But let's say this is the best complexity the literature is able to establish. Okay. Now, by allowing collaboration between gradient descent and Langevin diffusion, we can reduce that complexity to be of order log 1 over epsilon.
Ah, I see. So what is the meaning of complexity in Langevin diffusion? You want this diffuser to come into the epsilon ball and then stay there, or you just want it to come for the first time into the epsilon ball?
Great. So it's actually a high probability bound. So it's what's the probability that my xn is epsilon close to the high probability ball. So the probability that this is epsilon close with a probability that is larger than 1 minus delta. So delta is any user specified tolerance level.
I see. So this means that it is like a linear convergence. So are you also assuming some kind of local strong convexity?
Great, yes. I need to, so the assumption I need to impose is that, first of all, there is a unique global minimum. For this algorithm to work, it cannot have multiple global minimum. It needs to have a unique global minimum. And I also require the function to be strongly convex in a small neighborhood of this global minimum.
I see.
This is essentially what facilitates that whenever my gradient descent is in that neighborhood, it will achieve a very fast convergence.
I see. I see. Nice, nice. This is nice. Thanks. I have a second question, which is slightly more technical. So you talked about the Lyapunov condition and how that implies the Poincar inequality with certain constants. I'm very curious about how the Lyapunov condition gives that inequality. I'm just not able to see that.
So how like they were able to build the Lyapunov function and the...
No, suppose I have a Lyapunov function. Suppose I find this Lyapunov function. How do I get this Poincar inequality out of it?
So this term in the Poincar inequality constant, right, happened to be actually the term in the generator of my Langevin diffusion. And if you see how this Lyapunov function is defined, it's also defined in terms of the generator of my Langevin diffusion. So it's just simple algebra by plugging this Lyapunov function to the generator. So if you see the Harry-Duchamp of the Langevin diffusion, is actually exactly the L2 norm of the gradient of my f function here. So it's just playing with the algebra. By having this first condition here, you can construct a proper bound for the Poincar inequality constant. Yeah. This is a very elegant result. It's actually established in Bakery et al. 2013.
Oh, okay.
Yeah. So it's this work that established the connection between the Poincar inequality constant and the Lyapunov function.
Thanks a lot.
I guess I'll go next. So I was curious about the non-convex optimization part that you mentioned towards the end. So is the algorithm, can it be modified to account for cases where you may not have access to the exact gradient, like something like stochastic gradient descent? And
yeah.
also you also need a comparison of the functions, right, to do the swapping? Is an approximate comparison sufficient, meaning that, so the function itself might be very hard to compute because it could be the sum of many other functions, and so it might be expensive to do that comparison. So I was wondering if there is anything that one can do there.
Yeah, that's a good question. So what Shrikant mentioned is that, well, in a lot of the applications, right, I might not have direct access to this objective function and the gradient. Because in a lot of data science applications, these objective functions are often expressed as some expectation, where the noise is the variation in my underlying data. So instead of getting access to these objective and gradient, I often can only use sampling-based method and use the sample mean as an approximation of my objective function and my gradient here. If I plug in these estimated objective function and gradient, okay, if I plug in the estimated gradient, this is often known as stochastic gradient descent. And if I plug in the estimate for gradient for my Langevin diffusion, this is known as stochastic gradient Langevin diffusion. So here, the same method can be applied. Okay. In particular, I would run the stochastic gradient descent and the stochastic gradient Langevin diffusion in parallel. And the only caveat is that now, exactly as you mentioned, because I'm evaluating this objective function with stochastic noise. So I want to be careful about when to swap. I don't want to swap too aggressively because a lot of those swapping might be mistakes due to the noise in my objective function evaluation. So the way to overcome this difficulty here is to inject an appropriate threshold. So only when the Y process yield a much lower objective function than the X process, I will swap the position of the two. So in this case, we can establish similar convergence rate as what I mentioned before. But the extra condition we need to impose is actually on the batch size. So if I'm using the sample mean to estimate the gradient, then I require the batch size in this gradient estimation to be depends on the epsilon accuracy level I want to achieve. Okay. And because of this extra sampling step, the total computational complexity would be the batch size multiplied by the number of iteration it requires. So now the complexity would be epsilon to the power -1 times log 1 over epsilon. But even in this case, I would say this is still way better than what people has established in the literature.
Very nice, thanks.
Daniel?
Hi, thanks Jing for the nice talk. I wanted to ask about how sensitive this whole story is to the mode of convergence that you're working with, the rate of convergence to equilibrium. So I guess you worked with this L2 distance corresponding to the Poincar inequality, but if you did something like log Sobolev, there should be a entropy convergence. There are transport inequalities for different notions of convergence. Should there be like a parallel universe for each one of these convergence modes, you think, or how would that change things?
I see. I haven't thought very carefully about that, but there's, so the bound we build are mostly for the spectral gap. So if other mode of distance between measures can be quantified through the spectral gap, then we should be able to derive similar results there. But if there's not a natural connection between the spectral gap and this mode of convergence or this distance between measures, then I think we would need some extra work there.
I see. Okay, thanks.
Yeah, I just had a, thanks for a good, excellent talk, Vijay Subramanian here. I had just a quick question on the slide that you showed about using stochastic gradient descent and stochastic Langevin. So you're using an absolute error criteria to decide the algorithm, the pseudocode that you had. Yeah. Yeah, you're using an absolute criterion to switch, but would there a relative criterion be more appropriate at times? If the values are, I mean, if you're stuck in if the two, I guess I'm thinking if you're.
Do you mean this threshold could be like in terms of instead of an absolute term, it could be a relative term?
Yeah.
Yeah, I think that might work. Actually, that might work better. So I didn't really go into the details about how to set the threshold here, but the threshold does depend on some knowledge of the local structure around the global minimum. I mean, in practice, we would say you would choose a small enough threshold, and in most experiments we do, it works well. But in theory, the threshold need to be chosen based on knowledge of the local structure. But I think if I do not have a good knowledge of the structure around the global minimum, then maybe a relative threshold would work better than the absolute threshold. Yeah.
Thank you.
And Jason?
Hi, yeah. My question is, what is hidden in the big O there? I mean, as an optimizer, those rates look way too optimistic.
Okay, yeah. So what is hidden in my big O here is actually a constant term that depends on the dimension of my underlying problem. Okay.
Is it exponential though?
Yeah, exactly. So the dimension of the constant here is actually exponential. The dependence on dimension is exponential. And the reason is because, so what I'm doing is running a Langevin diffusion. So in order for the Langevin diffusion to find the right neighborhood, this has an exponential dependence on the dimension, right? If I do not have any regularity condition or any knowledge of what the objective function landscape gonna look like, then the Langevin diffusion is essentially doing a random search in this big state space that I'm interested in. Then I can have a very yield conditioned area around the global minimum, so that this would essentially make my algorithm have a strong dependence on the dimension of the problem. And the higher the dimension of the problem, the longer it's gonna take for my Langevin diffusion to find the neighborhood of the global minimum. And this is actually also connected to the first part of my talk, because this has to do with the spectral gap of the Langevin diffusion. So essentially how long it's gonna take to explore this state space to find the right region is essentially also looking at the spectral gap of my Langevin diffusion.
Thank you.
Okay, so are there any other questions? Okay. Varun, go ahead.
Thanks, Jing. I have a very basic question. So when you move from the low temperature to the high temperature process, do you still need to keep the low temperature process around, and can you forget where it was? And then when you move back to that, you can just sort of start from where the high temperature was?
Sorry, I didn't fully capture the question. Maybe my internet was not good. Can you repeat the question again? Hello, Varun?
Varun, you're on mute.
Sorry, can you hear me now?
Yeah.
Okay, so I was asking, when you move from the low temperature process to the high temperature process, can you just forget where the low temperature process was, and just like start from the high temperature when you go back to it, or you still need to keep it around for like the sort of product form steady state?
Okay, yeah, so for the product form steady state, I need to do the swapping. So I need to move the high temperature process to the position where the low temperature process was at in order to keep the product form a stationary distribution. But for my second task, which is to solve a non-convex optimization problem, there, well, for the, you might ask, like, why do I need to move the high temperature process to the position of where my gradient descent is at? Could I just swap the gradient descent for the place where the Langevin diffusion is at? I think that would work for the task of solving a non-convex optimization problem. But for the sampling task, where I need to maintain the reversibility of the process, so to have that product form stationary distribution, I need to actually exchange the position of the two. And as I mentioned in the literature review part, there is a very similar idea, which is saying that I'm going to just run 1 copies of this diffusion process, but I'm going to occasionally change the temperature of this diffusion process according to, again, a Metropolis-Hasting type of rule, similar as what we did here. So that would essentially do what you are describing. Like, I do not need to keep track of these multiple copies of diffusion process. I only need to occasionally change the temperature of this process. But the drawback there is that whenever you want to evaluate whether you want to change the temperature or not, you need to evaluate a probability function. And that probability function actually requires knowledge of the normalizing constant of your target distribution, which I guess in most cases is essentially what we want to avoid when doing this type of sampling tasks.
I see. Thank you.
Okay, any other questions? So if there's no more questions, then that concludes today's seminar. Thank you again, Jing, for the great talk. And for the next week, we're going to have Mohsen Bayaki speak. He's from Stanford University. So, okay, I'm going to stop the recording right now. And if you want, you can still ask some informal questions.